AI and Game Theory. What kind of sparks can game theory and machine learning create? The author of this article, Wang Zijia, reviews and summarizes the cross-research work in the fields of game theory and machine learning in recent years, showing readers the latest research picture in this field. The term game theory may not be familiar to some people who are only dedicated to cutting-edge algorithms for machine learning. In fact, intentionally or unintentionally, the idea of game theory has always existed in many machine learning exploration processes. Whether it is the classic SVM or the popular GAN, these models have the shadow of game theory behind them. In recent years, with the development of machine learning, the scenarios in which machine learning is applied have become more and more complex, and some people have begun to consciously connect game theory and machine learning. In general, game theory plays three main roles in machine learning research. 1. Explaining the principles and ideas of machine learning models. 2. Establishing appropriate learning strategies. 3. Predicting the behavior of human participants during human-computer interaction. Based on these three aspects, this article first explains the basic concepts of game theory and how to explain some models in machine learning, then introduces the application of game theory in multi-agent reinforcement learning, MARL, and finally introduces a new branch resulting from the combination of game theory and machine learning, game machine learning. What is game theory? Strictly speaking, game theory is mainly a mathematical model that studies conflict and cooperation between rational decision makers. This definition is somewhat abstract, and it is difficult for people who have never been exposed to game theory to intuitively know what game theory is from the name, game theory. This word can be broken down and viewed. The word game often appears in scenes such as Go and War. If we look at the English word of game theory, then game theory is easy to understand. It is a discipline that studies how to play various games in this world reasonably. Specifically, the games involved in game theory can be mainly classified according to 5 characteristics. Cooperation, whether people in the game can join forces with others. Symmetry, whether players have the same goal. Information integrity, whether the decisions and movements of other players can be known. Synchronicity, whether players' actions are performed at the same time, or one player's action follows another player's action. And zero-sum, whether one player's score will cause another player to lose points. Take billiards, snooker, as an example. This game cannot cooperate with others. Non-cooperation. Players have the same goal. Hit the ball on the table into the bag according to certain rules. Symmetry. Players can know the movements of the opposite player. Information integrity. Each player needs to start his own shot after another player fails to hit the ball. Asynchronous. Because the number of red balls is certain to a certain extent, one player's score will lead to a decrease in the other player's score expectation. So this game is a zero-sum game. Based on these classifications, different methodologies can be applied to different games. For example, Nash equilibrium, explained later, is easier to achieve in symmetric games. It should be noted that game here does not necessarily refer to games in the traditional sense. As shown in the figure below, it includes many aspects. Many problems can be regarded as games, which are essentially interconnected with artificial intelligence. The ultimate goal of AI is to enable computers to play some of the games that humans are playing or will start to play. Take a look at the picture below. The fields studied by game theory are very similar to the fields studied by AI. Let's recall that AlphaGo, which made AI famous among the public, started from games to learn human thinking patterns. So when game theory meets machine learning, some wonderful chemical reactions will occur, explaining the meaning of some mathematical models, emerging some new directions for exploration, etc. Image source http://Euler, FD, CVUT, CZ/Predmeti/game theory/game theory and machine learning. Many concepts that appear in game theory have been cited in machine learning, and Nash equilibrium (NE) is one of them. This refers to a state in the game. In this state, if any player changes the current decision-making, while other players' decisions remain unchanged, they will not be able to get more benefits. In other words, if everyone tells other players their decisions, other players will not change their plans. At this time, NE is reached. This is very similar to the optimal solution in machine learning. For NE, the most classic example is the prisoner's dilemma, as shown in the figure below. In this example, two prisoners were caught. Both prisoners were arraigned separately and could not collude in advance. In this case, if one of the two prisoners confesses that the other has committed the crime, the one who confesses will be released, and the other will be sentenced to 10 years in prison. If both of them do not confess, they will each be sentenced to 1 year in prison. If they both plead guilty, they would each be sentenced to 5 years in prison. In this example, it is easy to see that the NE of this game is reached when both people give out to each other. In this state, anyone who changes their decision-making will face 10 years in prison. Image source https://towards data science. com/game theory and artificial intelligence 57A 7937 E1B 88. Traditional machine learning is mostly regarded as an optimization problem. What we need to do is to find an algorithm that can search for the optimal solution. However, the difference between machine learning and traditional optimization problems is that we hope that the model obtained through machine learning will not overfit the data, so that it can perform well in situations that have not yet been encountered. In other words, we want these machines to make predictions about unknown numbers. This requirement is generally called generalization. This is why many projects in deep learning require additional constraints on optimization problems. These constraints are called prior in some articles and are called regularization in optimization problems. Where do these regularizations come from? And how do we choose good regularizations? How do we deal with imperfect information? At this time, the idea of game theory is very important. Generalization is sometimes called structural risk minimization. In other words, we build a mechanism to handle generalization by building a strategy to reduce the risk of the training set without knowing the validation set data. In machine learning, especially classification methods, many familiar traditional methods have shadows of game theory. SVM can be seen as a two-person zero-sum game. This optimization type of machine learning algorithm can be seen as finding a NE. Each class selects a hyperplane. If this plane exists, it can best complete the classification task. Linear regression can be seen as a non-cooperative game, and each class hopes to have the lowest loss. AdaBoost can be seen as using cooperative and asynchronous game theory for online learning. Of course, the most obvious algorithm that embodies the game is the adversarial learning in GAN. Let's first review the structure of GAN. GAN has two parts, a generator and a discriminator, as shown in the figure below. The generator tries its best to fool the discriminator, and the discriminator tries its best to determine whether the image was generated by the generator. The original paper that proposed GAN stated that this is a min-max game, and the ultimate goal is to find the NE of this game. However, the paper does not clearly mention the classification of this game. Therefore, although GAN has the shadow of game theory, it does not completely inherit the advantages of game theory. Therefore, GAN is difficult to train, and it is difficult to judge whether the training results are saddle points. So now some research is beginning to focus on how to embody GAN into a more specific game thereby making the results better. For example, in GAN, generative adversarial network games, the author proposes a GAN game and clearly defines GAN as a zero-sum game. Image source, https://sigmoidal EO/beginner's review of GAN architectures / the process is very similar to a two-player game. In this game, our players, two models, challenge each other. The first one fakes samples to confuse the other player, while the second creator tries to get better and better at identifying the correct samples and repeats this game over and over again, updating the learning parameters in each iteration to reduce the total loss with more experience. The final purpose of training is to find the NE of this game. At this time, both models have completed their tasks to the greatest extent and cannot be improved. Any parameter update will lead to an increase in their own losses. Game theory and reinforcement learning, multi-agent reinforcement learning, MARL, reinforcement learning, RL, aims to make the agent, our model, learn through interaction with the environment, which can be virtual or real. RL was originally proposed based on the Markov process. We put the agent in an uncertain fixed environment and try to learn an optimal strategy through a reward/punishment mechanism. In the case of a single agent, this approach is proven to converge. However, if multiple agents are placed in the same environment, multi-agent reinforcement learning MARL, the situation is much more complicated. Suppose we are trying to use smart cars to improve urban traffic. At this time, the decision-making of each vehicle will affect the decisions and performance of other vehicles. For example, a conflict between smart cars and smart cars is likely to occur because it may be the most convenient for both smart cars to drive along a certain route, get the most rewards. MARL classification. In the above example, the agents tend to have a competitive relationship. In real life, the relationship between agents may be cooperative or semi-cooperative and semi-competitive, mixed. The complex relationships between agents and the influence between agents make MARL extremely complex. At this time, the introduction of game theory will make modeling much easier. In this case, we can regard smart cars as different players, and NE at this time represents the balance point between different smart cars. Specifically, MARL can be divided into 3 games. Static games. In static games, agents cannot know the decisions made by other agents, so we can think that the decisions of all agents are synchronized and are not affected by each other. Dynamic games, stage games. There are many different stages in dynamic games. Each stage is a stage game, and the prisoner's dilemma mentioned above can be regarded as one of the stage games. Repeated games. If the games in each stage of a MARL system are similar, it can be called repeated games. Image source, https://towards data science. com/modern game theory and multi-agent reinforcement learning system Z8C936D6, the 42 RL algorithm based on game theory, AlphaStar. At present, in addition to the theoretical role of game theory, RL algorithms based on game theory are also shining. For example, the development process of AlphaStar, which controls StarCraft, is full of game theory. As a game, StarCraft is like rock, paper, scissors. It is difficult to get a single best solution. It is always in the game. You must learn the current existing strategies and choose the best one. The algorithm AlphaStar refers to is the double oracle algorithm, do-algo. This algorithm sets the goal of finding the NE of the current stage game. The principle of do-algo is shown in the figure below. It uses a deep neural network for function approximation and iteratively calculates the payoff matrix, GT, of the subgame. This subgame is the stage games mentioned above. At each time t, each stage game, the response sigma consistent with NE is calculated and the optimal strategy pi is obtained. Then a new strategy is added to extend GT to GT plus 1, and the above process continues to be repeated. Take the following figure as an example. The initial profit matrix GT of the two players is very similar to the prisoner case just mentioned. Pi represents the strategies that each player can adopt. In the initial GT, each player has only two strategies. For example, two players each have two attack plans: feint and attack to split the mines. Then, by finding the NE response, the best responses P1 and P2 that the two players can get in this scenario are obtained. At this time, both players found that they were not very confident in the existing attack plan and hoped to drag it into the later stage. So the players continued to select strategies from their own strategy libraries and added them to GT, such as opening a mine, thereby obtaining GT plus 1, and then the corresponding P1 and P2 were calculated at this time. In general, calculate the NE response in the current stage game, then expand the game according to the situation, and then calculate again until you become confident in the results. Image source: https://medium.com/@gemma pareno Piqueras/A Unified Game Theoretic Approach to Multi-Agent Reinforcement Learning 4B 291B 786,446. Of course, StarCraft is much more complicated than what I am talking about now, and the strategies are much more varied. For example, if you really choose to delay the late game, how to choose late game units. Whether they are very fleshy and powerful units such as Broodlords, Thunder Beasts aircraft carriers, Storm battleships, Thors or battlecruisers, or auxiliary spell-casting units such as Flying Snakes, high-level Templars, or Ghosts, and how to exchange mid-term units with the opponent so as not to cause excessive losses to yourself. These are all issues that need to be considered. So if you directly apply do-algo to a game like StarCraft and use actions as strategies in do-algo, there will be many strategies. Therefore, in the core algorithm document, a unified game theoretic approach to multi-agent reinforcement learning used by AlphaStar, they generalize the do-algo policy space response oracles PSRO. The strategy will no longer only be a single action, but can also be tactics or other meta-solvers. Deep cognitive hierarchies, DCH, were also proposed to solve the problem of strategy scale in the game. Among them, PSRO is shown in the figure below. The algorithm first samples an initial strategy and calculates the utility function and initializes the meta-strategy, a function that records the strategy distribution. The metagame starts with a single strategy and adds strategies. That is the oracle in the name of the algorithm. In each epoch, these strategies will respond to the meta-strategies of other players as much as possible. Note that this algorithm has a computational problem since, for each epoch, each player and episode, a new policy pi and a meta-policy need to be calculated on a per-player basis. Instead of calculating the exact best response, RL is used to calculate an approximate best response. Image source: https://medium.com/@gemma pareno Piqueras/A Unified Game Theoretic Approach to Multi-Agent Reinforcement Learning 4B 291B 786,446. Each step of reinforcement learning may take a long time to converge to good results, and some things that have been learned may be learned again in the subsequent learning process. In order to solve PSRO, in order to solve the problem of excessive calculation amount, this paper also proposes the DHC algorithm to parallelize PSRO. Specifically, instead of training epoch by epoch, K levels are predetermined instead of epoch, and NK threads are started. N is the number of players. Each thread trains an oracle for one player and saves the results to the central storage regularly. Each thread will also have policy information at the current level or lower level, similar to how subsequent epochs know the training results of the previous epoch. It can be seen that DHC sacrifices accuracy, reduced number of epochs, in exchange for its scalability, reduced computational effort. Source: https://arxiv org/pdf/1711 00832. PDF. It can be seen that this algorithm is the product of a close combination of game theory and RL algorithms. It has been applied in AlphaStar and achieved great success. It can be seen that the RL learning strategy represented by game theory is very trustworthy. Simplification of the amount of computation when the system has a large number of agents modeling may become very difficult, because the increase in the number of agents will exponentially increase the number of interaction methods between different agents. In this case, the mean field games proposed in game theory provides currently the best solution for MARL model modeling. MFG assumes that the activities of each player are similar, so if an RL scene can be converted into an MFG scene, it can be assumed from the beginning that all agents have similar reward equations, which can greatly reduce the complexity of the MARL model. Many papers have been studying this. Among them, Reinforcement Learning for Mean Field Game explores how to find the mean field equilibrium, MFE, in an action-coupled random game environment. It is assumed that the influence of other factors can be determined by the distribution of action means, and that all agents know the distribution of actions and use the recent best responses to select the optimal forgetting strategy. This paper proposes a mean field game reinforcement learning method based on posterior sampling, in which each agent extracts a transition probability from the previous transition matrix. The paper proves that the policy distribution and behavior distribution converge to the optimal forgetting strategy and limit distribution respectively, and together form an MFE. Game machine learning. There is also a concept in game theory called inverse game theory. Game theory aims to understand the dynamics of a game in order to optimize the possible outcomes for its players. Inverse game theory, in contrast, aims to design games based on the player's strategies and goals. Inverse game theory is useful in multi-agent AI and human-computer interaction AI. At the 2013 International Conference on Artificial Intelligence, ACI, Dr. Liu Tian's team from Microsoft Research Asia proposed the concept of game machine learning for the first time. This is a new branch that combines game theory and machine learning. It uses game theory ideas to explicitly model human dynamic strategies and uses a combination of behavioral models and decision-making models to solve this type of problem. With game machine learning, our algorithm can think one step more than humans, or even many steps more, and predict in advance what kind of reaction the other party will make so as to gain an advantage when playing games with it. Dr. Liu Tian wrote in an article introducing game machine learning, "Real human behavior is neither random nor completely rational and antagonistic. In fact, human intelligent agent behavior often follows certain rules. Unlike the previously mentioned technologies, game machine learning uses such a simple common sense. Both the interaction between people and the interaction between people and computers can be modeled so that we can know how these artificial data are generated and use them in the learning process, so as to gain an advantage in the process of playing games with humans." It can be seen that game machine learning can be applied in many fields such as advertising bidding, social media crowdsourcing management, and traffic guidance. Once we learn and describe the human behavior model in the machine learning process, we can know how people's behavior will change after our algorithm mechanism changes, and thus know whether the results we obtain will be good or bad after a long time, when human behavior tends to be stable, equilibrium state. In a game-theoretic machine learning approach for revenue maximization, in sponsored search, Dr. Liu Tian used game-theoretic machine learning to achieve good results in advertising bidding tasks. As can be seen from the picture below, this algorithm uses a two-layer optimization framework to learn the auction mechanism. Figure source, https://arxiv org/pdf/1406/0728 PDF. The specific algorithm is shown in the figure below. First, a Markov model is learned from historical data to describe how advertisers respond to the auction mechanism to change their bids. Then, for any given auction mechanism, the learned model is used to predict its corresponding future bid sequence. The auction mechanism can then be learned through empirical revenue maximization of the predicted bid sequence. The results show that when the prediction time approaches infinity, the returns will converge, and the genetic algorithm can effectively optimize this return. The experiments in this paper show that the proposed algorithm can produce a more efficient auction mechanism compared with several benchmarks. Image source, https://arxiv org/pdf/1406/0728 PDF summary. What is artificial intelligence? To solve this problem, we first need to propose a definition for intelligence. If past research on individual intelligence gave computers an intelligence quotient, IQ, then social intelligence corresponds to the emotional intelligence, EQ, of artificial intelligence. Finally, I quote this sentence from Dr. Liu Tian: "The introduction of game theory allows agents to learn how to deal with other agents and how to deal with people based on their past dealings with the environment." Similarly, game theory is a theory that studies various games, people, society, economy, etc., and its ideas are almost everywhere, not only in those algorithms that are explicitly proposed to combine game theory, but also in some common algorithms. The shadow of game theory ideas is often hidden. Perhaps game theory is also a bridge connecting machine learning to people and society. Game theory is one of the most fascinating fields of mathematics, influencing several different fields such as economics, social sciences, biology, and obviously computer science. There are many definitions of game theory, but I think this one is very helpful even if it is overly simplistic. Game theory is probability with incentives. Games play a key role in the development of artificial intelligence. For starters, game environments are becoming a popular training mechanism in areas such as reinforcement learning or imitation learning. In theory, any multi-agent AI system undergoes gamified interactions between players. The branch of mathematics on which the principles of games are constructed is none other than game theory. In the context of artificial intelligence and deep learning systems, game theory is indispensable if a multi-agent environment is to have some necessary and important capabilities. In a multi-agent environment, different AI programs need to interact or compete to achieve goals. The history of game theory is inseparable from the history of computer science. Much of the current research in the field of game theory can be traced back to the work of computer science pioneers such as Alan Turing and von Neumann. The Nash equilibrium, made famous by the movie A Beautiful Mind, is the basis for many AI interactions in modern systems. However, using game theory principles to model the AI universe many times over is beyond the realm of Nash equilibria. To understand how to use game theory to build AI systems It's best to first understand the types of games we commonly encounter in social or economic interactions. We engage in hundreds of interactions based on game dynamics every day. However, the architecture of a gamified environment is completely different, and so are the incentives and participants' purposes. How can these principles be applied to AI agent modeling? This difficult problem drives certain areas of AI research, such as multi-agent reinforcement learning. Obviously, games are the most visible entities of game theory, but they are far from the only space in which game theory concepts can be applied. That said, there are many other fields that have been influenced by both game theory and AI. Most scenarios that require multiple participants to cooperate or compete to complete a task can be gamified and improved using AI technology. Although the previous statement is a generalization, I think it conveys a message. Game theory and AI are a way of thinking about and modeling software systems, not just a technology. AI scenarios that leverage game theory should involve more than one player. For example, a sales forecast optimization AI system like Salesforce Einstein is not a perfect scenario for applying game theory principles. However, in a multi-agent environment, game theory is significantly different. Constructing game dynamics in an AI system requires two steps: participant design. Game theory can be used to optimize participants' decisions to obtain maximum utility mechanism design. Inverse game theory mainly designs games for a group of intelligent participants. Auctions are a classic example of mechanism design. So what games do data scientists in the AI era need to understand? Are there any connections between these games? The author of this article, Jesus Rodriguez, chief scientist and managing partner of Invector Labs, expressed his views on this. This article was written by Jesus Rodriguez. 5 types of games data scientists should know. Suppose we are building an AI system that requires multiple agents to cooperate and compete with each other to accomplish a specific goal, a classic scenario from game theory. Since its inception in the 1940s, game theory has focused on modeling the most common patterns of interaction that we now see every day in multi-agent AI systems. Understanding different types of game dynamics in the environment is a key element in designing efficient gamified AI systems. At a high level, the 5-element criterion helps understand game dynamics in an AI environment, namely symmetric vs asymmetric perfect information, vs imperfect information, cooperative vs non-cooperative, simultaneous vs sequential, and zero-sum vs non-zero-sum. The following will introduce them one by one. The 5-element standard proposed by the author. Symmetric vs asymmetric. One of the simplest ways to classify games is based on symmetry. In a symmetric game environment, each player has the same goal, and the outcome depends only on the strategy. Chess is a classic symmetrical game. Many scenarios we encounter in the real world lack the mathematical elegance of symmetry, because the participants often have different or even conflicting goals. Business negotiations are asymmetric games in which the parties involved have different goals and evaluate the results from different perspectives. For example, winning the contract vs. minimizing investment, perfect information vs. imperfect information. Another important way to classify games is based on the type of information available. A perfect information game is one in which each player can see the actions of the other players, such as chess. In many modern interactive environments, each player's actions are hidden from others, and game theory classifies these scenarios as imperfect information games. From card games like poker to self-driving cars, imperfect games are all around us. Cooperation vs. non-cooperation. In a cooperative game environment, different players can form alliances to maximize the final outcome. Contract negotiations are often thought of as cooperative games. In a non-cooperative game environment, players are prohibited from forming alliances. War is the ultimate example of a non-cooperative game. Simultaneous vs. sequential. In a sequential game environment, each player knows the opponent's previous actions. Board games are inherently sequence games. In simultaneous game scenarios, both parties can act simultaneously, such as securities trading. Zero-sum vs. non-zero-sum. A zero-sum game is one in which one party gains and the other party loses, such as a board game. In non-zero-sum games, multiple players can benefit from the actions of other players. In economic interaction, multiple participants cooperate to expand the market size, which is a non-zero-sum game. Nash equilibrium symmetric games rule the AI world, most of them based on one of the most famous mathematical theories of the 20th century. Nash equilibrium. Nash equilibrium is named after American mathematician John Forbes Nash. Essentially, a Nash equilibrium describes a scenario where each player chooses a strategy, and when one player does not change his strategy, no player benefits from changing his strategy. The late American mathematician and economist John Nash. Nash equilibrium is an elegant and powerful mathematical model that can solve many game theory problems, but it is limited in some symmetric game environments. For starters, the Nash method assumes that players have unlimited computing power, which is rarely the case in real-world settings. Furthermore, many Nash equilibrium models cannot account for the concept of risk, common in most asymmetric game scenarios such as economic markets. Therefore, many asymmetric game scenarios are difficult to achieve using Nash equilibrium. This is particularly important in multi-agent AI systems, which require finding the right balance between mathematical elegance of the solution and feasibility of the implementation. New ideas in game theory that are influencing machine learning multi-agent AI systems are one of the most fascinating areas of the AI ecosystem. Recent advances in areas such as multi-agent systems have expanded the boundaries of game theory, which relies on the most sophisticated ideas in the field. Below, the author provides further examples of game theory subfields that appear in modern machine learning. Mean field games, MFG, is a relatively new field in game theory. MFG theory was born in 2006 as one of a series of independent papers published by Minnie Huang Roland Malhamé Peter Keynes, Jean Mitchell Lasry, and Fields Medal winner Pierre-Louis Lyons. Conceptually, MFG includes methods and techniques for studying differential games in large groups of rational players. These agents not only have preferences for their own status, such as wealth assets, but also for the distribution of other agents in the group. MFG theory studies generalized Nash equilibria for these systems. A classic case is how to make several schools of fish swim in the same direction in a relatively coordinated manner. Theoretically, this phenomenon is difficult to explain, but it is based on the fact that fish respond to the behavior of their nearest neighbors. Specifically, each fish does not care about the other fish, but it does care about the nearby school of fish moving uniformly as a whole. If we put it in mathematical terms, the response of fish to a school of fish is the Hamilton-Jacobi-Bellman equation, HJB equation for short. The action of the entire fish school is the set of actions of all fish, which corresponds to the Fokker-Planck-Kolmogorov equation. Mean field game theory is a combination of these two formulas. A classic case of fish swimming uniformly in the mean field game Stochastic games date back to the 1950s and were proposed by Nobel Prize winner Lloyd Shapley. Conceptually, a stochastic game is performed by a finite number of players in a finite state space, and in each state, each player chooses one from a finite number of actions. The final combination of actions determines each player's reward and the probability distribution of the next state. The late mathematician Lloyd Shapley, who originated the concept of stochastic games. The classic form of a stochastic game is the philosopher's dinner problem. N+1 philosophers, n greater or equal to 1, sit at a round table with a bowl of rice in the middle and a chopstick between. Any two adjacent philosophers within the reach of both of them. Since the table is round, there are as many chopsticks as there are philosophers. In order to eat the rice in the bowl, each philosopher needs to get 2 chopsticks within reach. If one scientist eats it, his 2 neighbors cannot eat it at the same time. The life of a philosopher is very simple, only thinking and eating. In order to survive, a philosopher must think and eat again and again. The task is to devise a mechanism by which all philosophers can survive. A classic case of philosopher's dinner in stochastic games. Evolutionary game theory, EGT, draws inspiration from Darwin's theory of evolution, EGT, whose origins date back to John Maynard Smith and George R. Price in 1973, can also be analyzed as a strategy, a mathematical criterion that can be used to predict the outcomes of competitive strategies. Conceptually, EGT is the application of game theory concepts to a scenario where a population of agents uses different strategies to create stable solutions over time through the evolutionary process of selection and replication. The main idea of EGT is that many behaviors involve the interaction of multiple agents in the group, and the results of any agent are inseparable from the interaction between its strategy and the strategies of other agents. Classical game theory focuses on static strategies, i.e., strategies that do not change over time, while evolutionary game theory focuses on changes in strategies over time and on the dynamic strategies that are most successful during evolution. A classic example of EGT is the hawk-dove game, where a hawk and a dove compete for shared resources. In this game, each player strictly follows one or all of the following strategies. Eagle: initiate an aggressive behavior and never stop until injured or until the opponent retreats. Dove: if the opponent initiates an attack, retreat directly. If we assume that there are the following situations. 1. When 2 individuals initiate an aggressive behavior, the battle will eventually end, and both have the same probability of being injured. 2. The cost of combat reduces the health of the individual by a certain constant C3. When the hawk and dove meet, the dove runs away directly, and the hawk obtains the resource 4. 2 doves meet the resource and share it equally. Then the health of the hawk-dove game is as follows. Inverse game theory. In many cases, there is no need to optimize the strategies of the participants, but to design the game around the behavior of rational players, which is inverse game theory. Auctions are considered a prime example in inverse game theory. In short, with the development of artificial intelligence, game theory is experiencing a renaissance. Game theory principles developed by computer science legends such as Alan Turing or von Neumann are now at the core of some of the world's most intelligent systems, and recent advances in artificial intelligence are helping to advance game theory research. As AI continues to evolve, we will see more new ideas from game theory find their way into mainstream deep learning systems.